window.
Okay, so you're still not able to get onto Blackboard?
Yeah, I'm not. I'm just gonna call the technicians tomorrow morning and see if they can give me some type of assistance.
Okay. Okay, that would be the preferable way to do it because at least until we go back on campus. When we go back on campus, I'm going to change everything back to the way that I thought was best for teaching this class. But as long as we are still in this virtual world, what I have to do is grade the homeworks through Blackboard. And any corrections or points that I deduct, I put little comments on the Blackboard so that the student can log in and see, what the issue was. So that's the preferred way to do it. If you can't get this resolved by midnight tomorrow night, then just email me your homework and I'll grade it that way. But it would be most preferable if you can get into the system.
Okay. Yeah. For some reason, why I asked them yesterday, and they said it should take up to like 7 hours. So I waited till the day to log back in. Tried again today, had the same issue. So I'm just gonna call them and see if they can manually do it for me
Okay.
and see if that works. But thank you again.
Okay. Yeah, no problem. I mean, if worst comes to worst, and this applies to anybody who has Blackboard issues, worst comes to worst, just make sure you email me, and it has to be a PDF. Email me the PDF before midnight, and we'll do it that way. But it's preferable to have it in the system because then that way I can give you feedback.
Perfect. Thanks again.
Okay. Anybody else have any questions you'd like to ask of anything before we start tonight's lecture? Alrighty. So I assume everybody can see the screen. Let's get started. Okay, so tonight's lecture is concerning flexural analysis of beams. So we're going to kind of continue the trend. We're dealing with reinforced concrete, but we're starting the whole discussion of how to design reinforced concrete with flexural members, basically beams that are resisting applied moments. That's where this course is starting. So a flexural analysis of beams, we're talking about reinforced concrete, is designed by the strength design method. Strength design compares a reduced nominal capacity based on material mechanics to a factored load design. That's how we do it. That's how we design our stuff. So basically what we do is we calculate to the best of our abilities what we think it would take to utterly fail a beam section. And then that's our nominal strength. And then we put a factor on that to account for accidental, maybe the rebar wasn't put in the right space, maybe the concrete didn't quite come up to strength. We have a factor on the nominal capacity that is less than 1 to reduce the nominal capacity to give us a little bit of a factor of safety. And then we take the loads that we anticipate our structure needs to support, and depending upon the source of the load, we will factor that load up. So for instance, dead load, which is the weight of the beam, a concrete slab, anything that's a permanent part of the building, the dead load will get a factor of 1.2. So it's a 20% bump for dead load. But dead load, we can account for dead load pretty accurately. Live load is much more ambiguous or just kind of generated by a committee on what the live load should be, which may or may not reflect what it really is. So the load demand load factor on live load is 1.6, 60% bump to account for the uncertainty of what the live load may be during the life of the building. Okay, so that is in a nutshell what strength design is. We calculate to the best of our ability what the capacity is, and then we reduce it a little bit. And then we calculate what the demand is, and we factor that up actually quite a bit. And then we compare the two. And if my reduced capacity is still greater than my amplified demand, then the beam is acceptable to be used in a building. So phi, the Greek symbol phi is a number less than 1 that represents a resistance factor to account for probabilities that the capacity is short of what was expected. M sub n represents the nominal flexural capacity of a reinforced concrete beam found from the mechanics of materials. So the way that reinforced concrete generally works is you have a capital letter that represents what it is you're talking about. So capital M represents a moment or flexural capacity. A capital V will represent shear. A capital T represents torsion, so on and so forth. The little n, so we say M sub n, the little n represents a nominal capacity. So again, nominal capacity is what we expect the capacity to be based on the material properties. M sub u represents the factored or increased demand from anticipated loading. Factoring varies based on the source of load and is derived from statistical probabilities. So again, capital N, M means that we're talking about moments or flexural capacity, and sub U, so M sub U represents, the U is ultimate. So that represents your demand, okay? So when you see M sub N, you're talking about capacity. When you see M sub U, you're talking about the demand. And then ultimately, strength-based is based on the comparison of phi mn. Phi mn is the reduced capacity that must be greater than mu, which is the amplified load effect. So this is the holy grail of strength design. And please make note, I'm going to repeat this probably about, I don't know, 12 or 1400 times. In all the calculations that you do for this class, most of your calculations will get to the point where you're justifying this expression. But if you do not show this expression, then all of your calculations are for naught. Okay? You're going to build up to the point where you can confidently say that phi mn is greater than mu. But if you don't actually do this comparison, phi mn is greater than mu, you haven't finished the problem. You haven't proven that you actually have capacity, okay? This is going to make a lot more sense when we get to more elaborate type problems where you do maybe a few pages of calculations and you think you're done. I'm just saying, please always remember you're not done until you go back and actually calculate phi mn greater than or less than mu. This is what you need to get to. Any questions so far? Okay. Reinforced concrete was originally based on a working stress design. They called it WSD. ACI 318. ACI 318 is that code book that I showed you. You should have a copy of that for this class. But ACI 318 1956 is the edition that first included ultimate strength design as an appendix. So all the versions before 1956, which I believe go back to like 1910 or something like that, were all they had was working stress design method. So they introduced the ultimate strength design as an appendix in 1956. In 1963, the ultimate strength design method was presented equally with the WSD. In 1971, ultimate strength design became the primary design method, with the WSD being redelegated to an appendix. So really, since 1971 is when ultimate strength design was the primary way to design reinforced concrete. In 2002, ACI removed the WSD method from the code completely. It was eradicated. It was deleted from the code. ACI 318-2002 also saw the load factors revised to match ASCE 7 factors. So prior to that, ACI always had their own set of load factors. And then everybody else used this document, ASCE, American Society of Civil Engineering. Everybody else, being timber, masonry, steel, everybody else used ASCE 7 factors, while concrete was still using ACI factors. And that was a real pain in the butt. I remember it. I was doing work at that time, and it was a real pain in the butt when you got loads from a steel structure that is attached to and supported by a concrete structure, which is then supported by soil. And you had to run all those load factors down from the steel and then change them all to concrete factors. Okay, well, we don't have to worry about that now. Now, everybody uses the same ASCE 7 load factors. Okay, so that's a brief history of how we got to where we are. So now, how do we actually design a beam? Concrete, as I've mentioned, follows a fairly linear stress strain curve with the slope of E sub z up to about approximately 40% of F prime C. At higher stresses and strains, the concrete is considered to have gone plastic, and the expressions must be developed to capture this behavior, as we talked about in the last lecture. So if I look at a beam from the side that has some kind of internal moment, M sub x, looking at the side view of a beam with a flexural moment applied, then if I look at the strain condition, we draw the strain condition. At failure, ACI 318 section 22.2.2.1 prescribes the maximum strain as 003. Okay, so if you guys ask me, why is that 003? Where did that come from? This is where it came from. ACI 318 section 22.2.2.1 tells you it has to be 003. So this point on the strain diagram is fixed, this point right here at 003. ACI section 22.2.1.2, the next section, says that the strain in the steel or at any other location is proportional to the distance from the neutral axis as labeled distance C from the top of the beam. So all that's saying is that this point here is 003. The point where you have the neutral axis or zero strain is defined as little c from the top of the beam to the neutral axis. And the strain at any other location, say at the level of steel, any other location is defined by this triangle and the straight line. So basically everything else is proportional to this triangle here, defined by a height of little c and a maximum strain of 003. ACI section 2.2 defines epsilon t as the strain in the layer of steel furthest from the neutral axis or closest to the bottom of the beam. Epsilon s is the strain at the centroid of the steel. Now, I know this is going to be a lot of information and it takes a little bit of time to soak in, but please note there is a difference between epsilon t and epsilon s in definition. Epsilon t is the layer of steel furthest from the neutral axis. Epsilon s is the strain at the centroid of the steel. If you only have one layer of steel, like is shown in the illustration, then the strain at that one layer of steel is epsilon t and epsilon s. They're the same thing. They are the layer closest to the bottom. They are also the centroid of the steel. But if you have multiple layers of steel, then epsilon T and epsilon S are not the same thing. One is the lowest layer, the other one is the centroid of all the layers. ACI 318 section 9.331 prescribes the minimum strain for epsilon T as 0.004 inch per inch, thus mandating that the steel has fully yielded at the point of concrete compressive failure, which is 0.003, as I just mentioned. So 0.004 is the lowest strain that we can design to in the steel. And remember, grade 60 steel yields at 0.0207. So 0.004 is quite a bit larger, almost twice the yielding strain for the steel. So we'll get into this a little bit more, but basically the code says that for a beam, doesn't apply to columns, but for a beam, 0.004 is your absolute minimum. If you calculate what your strain is and you get a number less than 0.004, well, you need to redesign the beam because it doesn't meet the ACI requirements. The distance from the top of beam to the centroid of the flexural steel is labeled little d, as I've labeled right here. So little d is always defined is the top fiber or the fiber that hits 0.003 to the centroid of all your steel if you have multiple layers of steel. Doing okay so far?
Yes.
Okay. ACI section 22.2.1.1. And I know I'm throwing a lot of sections at you here, but I do encourage you to either revisit this lecture on YouTube or download the PowerPoint and go back over it when you have time and look up some of these sections. They're actually very important that you know where to find them in the code and what the code says about these things. That's why I've given you so many section references so that you can go back later and find these things. Also, when you read the textbook, which is absolutely essential that you read the textbook, because even with a 2-hour lecture, I really can't even scratch the surface of what they can present to you in the textbook. So when you read the textbook, you will see a lot of cross-referencing. They do the same thing. They tell you what ACI says and where ACI says it so that you get the whole picture. Okay, so all of this information, it's a lot of information. This is a accelerated course. We only have 10 weeks to do this, so it's going to be flying at you at 70 miles an hour. But that's why I'm giving you all these section references so that you can go back and find these things and investigate them. So ACI 318, 22.2.1.1 states that equilibrium must be maintained, which means that the tension here in the bottom must equal the compression at the top. For static equilibrium, all the forces in the x direction have to equal 0. So if this is a flexural beam, then T has to equal C. Oh, and by the way, I've added this diagram here. This is the stress diagram. If this is strain, then this is stress. And on the stress diagram, you'll notice that I didn't draw that parabolic curve this time. I drew a boring, simple rectangle. That boring, simple rectangle representing the stress in the concrete is allowed by section 22.2.2.4 that allows for the Whitney stress block assumption to be used to approximate the summation of compressive stresses at epsilon Cu equal to 0.003. So what did that mean? What that means is at a strain of 0.003, you can assume this rectangle instead of the parabolic curve that I showed you last lecture. If you're trying to find or summate the forces at a strain of anything other than 003, this Whitney stress block doesn't work anymore. It's only calibrated for this maximum strain of 003. Okay, so ACI 222241 states that the effective stress of the Whitney stress block is assumed to be 0.85 F prime C. So the magnitude of stress in the stress block is always 0.85 F prime C, right? So whatever F prime C is, 4,000, 6,000, 10,000, whatever it is, you just plug it in and you have the magnitude of the stress in the Whitney stress block. This is a side view or a section view of the same beam in the same stress condition. And what I'm showing in this section view is that this compression block is of a depth little a, which is not equal to C, but it's a depth of little a and a width of B. So the whole available width of the beam is in compression, and the compression of this stress block goes down a distance of little a. The uniform stress is distributed over the width of the beam, B, and over a depth equal to A. In this class, in this ACI design, some of these variables are pretty consistent. So again, little c is always from the extreme fiber to the neutral axis. Little d is always from the extreme fiber to the steel. Little a is the extreme fiber to the depth of the Whitney stress block. And B, in some way, shape, or form, we have B sub F, B sub W, B sub effective, but B is always a measure of the width of something that's in compression. Okay, ACI 318, equation 222241 defines little a is equal to beta 1 C, where beta 1 is a factor based on concrete strength and little c is distance to the neutral axis. So little a and little c, or just a and c, are always proportional to each other. There's a direct relationship of proportionality of beta 1, but beta 1 itself is a function of the strength of concrete. ACI table 222243 defines beta 1 as if your strength of concrete is between 2,500 and 4,000 psi, beta 1 is 0.85. If you're between 4,000 and 8,000, it is this expression, 0.85 minus 5/100 of F prime C minus 4,000 over 1,000. And if you have concrete over 8,000, then it's just equal to 0.65. So that's beta 1, very important. Let's see. Where did I put that? Bear with me. I'll be back in a second. Yeah, let me grab my textbook. I'll be right back. Okay. You can also find in your textbook, at the back of your textbook, starting on page 593, there are a number of helper little charts and things. And now's as good a time as any to bring your attention to some of these. So if you have your textbook, go ahead and open it to page 593. And you'll see that this is called Appendix A. Appendix A has a lot of really useful information. Table A.2 on 593 is another resource for you to look up what the diameter and cross-sectional area of all the standard rebar sizes are. Now, if we kind of jump ahead here a little bit, let's see, where did they put that? Here we are. Go to page 598, table A.7. And this table has quite a bit of information, and there's quite a few good resources that we will get back to this later on. But the thing I want to point out right away is at the very top, each column heading is headed by 3,000 PSI, 4,000 PSI, 5,000, 6,000. So we only have 4 strengths of concrete here, but for those 4 strengths, you will notice just below that they say beta 1, 0.85, beta 1, 0.85, beta 1.8, and beta 1.75 for 6,000 PSI concrete. So we're going to go back to these appendix and these tables like almost every time we meet. But this is the first intro to this on page 598, table A7. If you want a quicker way or you can't find this equation, then you can look it up in the headers of that table. ACI 318, section 22.222 prescribes that the tensile capacity of the concrete to be neglected in strength calculations. We said this last time, but this is the section where you can find it. And it's basically saying that on my stress diagram here, you see that there is no tensile stress due to concrete. It is just completely ignored. In fact, anything below this distance A is as if there is no concrete at all. There's no compressive stress, there's no tensile stress, there's no stress at all. It's as if the concrete only exists in this area of A and B and nowhere else for the purposes of strength calculation. Because the reinforcement is assumed, and not just assumed, but also prescribed, it's dictated. You will make sure that your reinforcement is yielding when your concrete hits 003. So epsilon Cu is the concrete strain at 003. The tensile force is equal to the area of the reinforcement multiplied times the yield stress. And this is good news because the yield stress, Fy, is given to you in every problem statement. And so if this were not true, you would have to do some additional calculations to figure out what the stress in the steel is. But you don't have to. The stress in the steel is guaranteed to always be at least the yield. So you don't need to figure that out. It's a give me. So as long as the problem statement tells you that it's grade 60 or grade 80, whatever the grade of that rebar is, you know what Fy is. Using the Whitney stress block, the compression force is equal to the effective stress multiplied by the beam width by the assumed depth. Okay, so C, big C, the compressive force, is equal to the magnitude of the stress, which is 0.85 F prime C, times the area. The area is a width times a depth. So the compressive force is 0.85 F prime C B A, which A, as we just said, is equal to beta 1 times C. So I can substitute that in here and say that the compressive force is also equal to 0.85 F prime C little b beta 1 C. The compressive force is assumed to act at the centroid of the compression block or at a distance A/2 down from the top of the beam. So the depth of this block is A, the compressive resultant is at A/2. Again, D is the distance from the top of the beam to the center of the steel. For beams with multiple layers of reinforcement, D is measured to the center of gravity of the total tension steel. And since the sum of forces in the x direction is equal to 0, T then is equal to C T is equal to the area of steel times the stress in the steel, so ASFY. The compression, as we just noted, is equal to the stress in the concrete, 0.85 F prime C, times the area, which is BA. Solving for little a, so I can rearrange, solve for a and rearrange this, I get a little a is equal to ASFY over 0.85 F prime C B. If I sum moments about C, which is the centroid of this block, so if I sum my moments about C, then I have that the capacity, M sub n, the capacity of the beam, is equal to the force T, which is applied at the center of the steel, times a distance of D minus A over 2. The tensile force, as we noted, is ASFY. So the capacity is also ASFY times D minus A over 2. And little a is this product here. So the capacity Mn is also equal to ASFY, parentheses D minus ASFY over 2. That 2 comes from the A over 2, 0.85 F prime CB. And the final form, the capacity Mn is ASFY D minus ASFY over 1.7 F prime C B. This is our basic equation for a singly reinforced beam. Now, I do want to caution you, this is a very powerful, easy way to get to a quick answer on the capacity of a beam in bending. But realize the limitations of this equation. This equation only is applicable if you have a single reinforced beam. And what that means is you don't have reinforcement at the top and you don't have a T-beam with T-beam behavior. It has to be a rectangular beam with only steel at the bottom. And then this equation is applicable. Any questions? All right. You guys ready for an example?
Let's do it.
That's what I like to hear. All right. Example number 1. Find the nominal flexural capacity of this beam. I use this beam a lot. So it's an 18 by 30 and the steel is located at 2.5 inches up from the bottom. So D is 27.5 inches, distance from the top fiber to the center of the steel. The concrete is given as a 6,000 PSI concrete. The steel is given as 4 number 8s, A706 grade 60 steel. Solution. So the area of the steel, I have 4 times 0.79 inches squared. Again, you can go to that appendix I just showed you in the back of the book if you don't have these memorized just yet. 1 number 8 is 0.79, so 4 times 0.79 gives you 3.16 inches squared. The tensile force is ASFY, which is the area of the rebar times the grade. The grade was given at 60, so 60 KSI, which gives you 189.6 kips of tensile force. The D dimension is 27.5 inches, as you can see here. The B dimension is 18. Therefore, I have all the information I need to plug into my capacity equation. This is ASFY, D minus ASFY over 1.7 F prime C B. Crank this through, you get 5,018 kip inches is the nominal capacity. Or most commonly, we will report the capacity and the demand of beams and flexure in kip feet. It's just a more industry standard way to report moments. So that would be 418.2 kip feet of capacity. And by the way, at the end of lecture 2 on Tuesday, remember I went through and I calculated the capacity of a beam using the polynomial equation that was a better simulation of the actual stress of the concrete in compression. And when we got to the end of that calculated summation, we got 418.2 kip feet. So as you can see, the simplistic method yielded exactly the same result as the more complicated and interesting method. That is not to say that you will ever see that again. This is the way we do it in concrete design. There are purposes for the polynomial method of doing things. I've used it in my practice many, many times for very good reasons. But usually the reason was that I was looking for the capacity at a concrete strain other than 003. And it wasn't for ultimate strength design, it was for more sophisticated things that I was doing. But if you're just looking for the code required nominal capacity at 003 as the code requires, this is how you do it. And you use the simplified Whitney stress block, and it's a lot quicker and simpler. Any questions on example number 1? Okay. So we're going to define a new variable. That's the Greek letter rho. So we are going to define rho as, and it's a ratio. Ratio rho is the ratio of the area of steel to the area of concrete. So it's not the gross area of concrete, as you notice. It is just the width of the beam times d, the distance from the top to the center of the steel. But that's how we define this. So rho is a measure of steel to concrete. The higher rho is, the more steel you're using. The lower rho is, the more concrete relative to steel that we have. So the ratio area of steel to concrete. Solving for A, then remember A was equal to ASFY over 0.85 F prime C B. So we can substitute in this expression for rho into here. So then A becomes, again, A is the depth of the Whitney stress block. A becomes rho FYD over 0.85 F prime C. If we solve for A sub S then becomes rho BD. And so phi min is equal to mu required capacity. Phi is the resistance factor. We're going to cover that in more detail later. And phi min is equal to phi AS Fy d minus A over 2. We just did this, which is equal to, now I can plug in, instead of AS, I can plug in rho BD. So instead of AS here, I plug in rho BD here. And instead of A, I plug in rho FYD over 0.85 F prime C here, okay? So what all I've done in this expression, this is the one we just did, but if every instance of AS has been replaced with rho. So this is absolutely equivalent. Then what I did here is I pull out all the common terms and put them out in front so that phi BD squared Fy rho times 1 minus rho Fy 1.7 F prime C, and this is equal to mu because phi min has to be equal to or greater than mu. Where we're going with this, why did I do all this math? Just kind of threw it at you. Where we're going with this is we're going to come up with a design tool so that if the area of steel was not given to you, like this example we just did, I told you it was 4 number 8s. But what if I didn't tell you it's 4 number 8s? What if I just told you I want this beam to support X amount of load? How would you size that steel? See, that's the difference between analysis and design. Analysis, you know what everything is, you just need to analyze it. But for design, you don't know what everything is. You need some tools to come up with a design method. That's what we're doing here. So if I define another new variable, r sub n, and r sub n is defined, it's created as mu, the load that you would like to carry, divided by phi bd squared. If I do that, then this expression here reduces to rho is equal to 0.85 f prime c over fy, 1 minus square root 1 minus 2 rn over 0.85 f prime c. Look, jumped ahead too quick. Let me go back. So what do we have here? What does this get me? Why is this important? Any ideas? You guys are awfully quiet. Anybody awake?
So for this one, if the area is not given, we need to use this formula, right?
That is correct. That's absolutely right. So if you don't know what AS is, which is the area of steel, but you do know how much you want to carry in moment, then you can plug in what you do know. I know F prime C, I know the grade of the steel, and I know B and D and MU, then I can plug them all into this equation to get a required rho, a minimum amount of steel required to be able to carry this moment. So I've derived a tool where you can plug in this index that is a measure of how much load you need to carry, and it will spit out for you a minimum amount of steel that you need to provide. Okay.
Since your demand load is technically hypothetical, right? You can like assume that it was this much that we're gonna need and how much row it's gonna be needed or something.
Yes. Yes. So MU, if I don't just flat out give you what MU is found from the tools that you learned in mechanics of materials, statics, possibly structural theory, where you learned how to analyze a structure and derive what the applied moments and applied shear. From those courses, you learned how to analyze a structure and get what your demands are. So this course is all about, now that I have my demands, how do I know how big I need to make the beam? Or how much steel do I need to put into the beam in order to satisfy those demands? So that's what MU is. MU is your demand. You need to provide a capacity phi min to satisfy that demand. But if you don't know how much steel you have, you can't calculate phi min from the equation that I gave you. So you need something to have an estimate of how much steel you're going to need to provide.
All right, that makes sense.
Great. Anybody else? Any other questions? We're going to jump into an example, but any questions on the theory before we do? Okay. Now, I do encourage class participation. I do feel that especially in this virtual environment. I can't see you guys. You can probably see me, but I can't see you. So I have no idea if everybody's sitting there at home, nodding their heads, going, yeah, 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 this is easy. This is simple. Move it. Let's move along. Get to something interesting. Or do I have 25 students with their eyes glazed over and their mouths wide open and drool coming out going, what the crap is he talking about? Or is it half and half? I have no idea. When I'm in a classroom, I can see the drool. So I know when to slow down and to poke at people until we get everybody caught up. I don't like to leave people behind and then get 4 lectures down the road and nobody knows what I'm even talking about. I can't see you in this virtual environment, so I cannot see if you're drooling or not. I have to rely on you telling me that there's a pool of drool under your chin and you need to slow down and let's go back over some things until we're caught up. Please tell me if I need to slow down. There's no problem slowing it. I don't have to finish every lecture on every day that I say I'm going to finish that lecture. That's not what's super important. What's super important is that I'm not leaving people in the dust who don't speak up. So when I stop, and I try to stop often, and I say, are there any questions? Is everybody getting this? Is anybody still alive? Is somebody catching flies with their mouth wide open? I need some feedback. Please tell me if I'm going too fast or slow. And if you need more time, if you don't want to say it vocally, chat it, whatever. But I have no problem going back. I just don't go back if nobody says anything. So with that, let's do example number 2. This is a design problem. As opposed to example number 1 was an analysis problem, example number 2 is a design problem. The design problem is find the required steel in order to support a load of 375 kip feet. We're going to use the same beam, 18 inches wide, 30 inches deep. The steel is located at 27.5 inches down, but I don't know how much steel I need. The concrete is 6,000. I know that the steel is going to be grade 60, and I assume I'm going to have a fee factor of 0.9 on this thing, but that's about all I know at this point. So how do I do it? What's my solution? I use the tools that we just derived. So I'm going to calculate my R sub n. That's equal to mu over phi BD squared. So I've got an mu 375 kip feet. Remember to always translate that into kip inches to be compatible with your units. So times 12 over phi of 0.9, B 18, D is 27.5. And don't forget the square. I can't tell you how many times people forget the square and are really off by a lot. This ends up being 0.367 KSI. So my equation for rho, I can plug in now what I know. F prime C is 6,000, Fy is 60,000. I can plug in 2 Rn is 0.67 KSI over F prime C is 6 KSI. So again, look at all of my units are consistent. I can't say this enough times. Make sure you always use consistent units. You like PSI? No problem. Just make sure everything is in PSI. When I calculate this in my calculator, I get a number 0.0635. When you're dealing with reinforcement ratios, these numbers get to be pretty small. So make sure you run these out at least 5 digits or so that you don't lose any necessary accuracy. So the required rho, remember, this is not what's provided, this is what's required in order to support this load. The required rho is 0.0635. Since the area of steel is equal to rho BD, then I can multiply this found rho times B times D to get to 3.15 inches squared. Now, here's where the design comes in. This is how much steel I need. I, the designer, I'm going to provide that with 4 number 8s. And here's where there may be multiple correct answers. You may be able to provide this with, say, 6 number 7s, or 8 number 6s, or 4 number 8s, or 4 number 9s, or 3 number 10s. There's no one answer here, but 4 number 8s is a very workable solution. So the area that I am providing is 4 times 0.79, which is 3.16 inches squared. Now, here is where the mistake happens. Many, many times. Other than missing the square here, probably the most common way to mess up this problem is to say my required steel is 3.15. The steel that I'm providing is 3.16. 3.16 is more than 3.15. Therefore, I have met the requirements of the code. No, you are not done yet. This is just a design. This is a trial. You're trying to use 3.16 inches squared. There's other things that we're going to talk about later on in this course that makes that this requirement is not exact. There are times when it gets you in the ballpark, but it is not exact. So therefore, you're not done. Why are you not done? Because you still have not proven to me that phi mn is greater than mu. And only then will you be done. So always recheck your answer and calculate phi mn. So this is a singly reinforced beam, so I can use my equation. 0.9, 189.6, 27.5 minus 189.6 over 1.7, 6,018 is 376.4 kip feet, which is greater than my demand of 375 kip feet. Now I can say that it is okay. Now I have proven that I've met the requirements of the code. Okay, this is a classic design problem. Any questions?
Yeah, Professor, what is Rn?
Rn is an index. It has no physical meaning. So it doesn't actually represent something that you can see, smell, or touch. It's just an index, but it's a very useful index in finding the required amount of steel, right? So R sub n is just an index of the moment over phi BD squared.
Okay, it's just a step for rho, basically.
Yes, sir. That is it.
And do we have any units for rho?
Rho does not have units because rho is a ratio of the area of steel divided by the area of concrete. Both of them have the units of inches squared. So the inches squared divide out, wash out.
Okay, thank you.
Okay, and then even in this equation here, you can see that the KSI is divided by KSI and the KSI is divided by the KSI. So even in this expression for rho, all the units wash out as well.
Okay.
Okay,
Professor,
yes.
for this type of problem, the resistance factor is always given, right?
The phi,
Mm-hmm.
usually it is not given, but I haven't really gone into full depth about how to calculate it. 99% of the time for a beam and flexure, it's going to be 0.9. So it's not something that needs to be given. That's just kind of like a standing order that it's almost always going to be 0.9. But there are exceptions to that, and we'll talk about those exceptions coming up here pretty quick.
Okay.
All right. Now, one other thing I can show you Oh, I'm sorry. Is there a question?
Yeah. So your choice of rebar, it was just an educated guess, right? Just to get around the same ballpark as what AS was.
It is. Yes.
And then, yeah.
So you need 3.15. It was an educated guess that got me pretty close to 3.15 with 4 number 8s. But you can also go to page 596, table A.4, and you can look in this table and you can see that it's like a matrix that has number of bars in the first column, and the first row is number 3s, number 4s, number 5s. And you can look in this table and you see from the table that 4 number 8s is 3.14. It's slightly different than what I did here because there's a teeny amount of round off error with the area of a number 8 bar here, but it's basically the same thing. So what you could do, instead of using intuition or experience, you could go to this table and say, okay, I need 3.15. With a number 7 bar, oh, I need 6 of them. With a number 8 bar, I basically need 4 of them. With a number 9 bar, I still need 4 of them. With a number 10 bar, I need 3 of them, so on and so forth. So table 8.4 will really aid you in this selection process of finding the number and size of steel.
Okay. So and then that's why you go back and recheck your answer just to make sure that everything is accounted for. Okay,
Yes.
that makes sense.
Yes, exactly. The other thing I want to bring to your attention is we have tables that does what these two equations do right here. So if you go to page 599, which is table 8.8, that's where they start. But you got to be careful because you got to look at the small print behind the table. On page 599, that is applicable for 40,000 PSI rebar, 3,000 PSI concrete. And that's not what we have here. So you can flip through these tables until you find what we have. And in this case, you can't use them because I have 6,000 PSI concrete. The table only goes to 4,000 PSI concrete. But I just wanted to make you aware that if the problem was 4,000 PSI and the rebar grade is 60, you could use table A13 on page 607. So there's many, many times where you can use these tables and it will speed it up a little bit. But if I give you some parameters here that are not represented in the tables, then you have to fall back to these equations.
Okay, so just when in doubt, cross-reference, and if you can't derive it from the table, just use the equations.
Yes, yes.
Got it.
Okay, let's see, ductility. Oh, okay.
Professor,
Yeah,
one more question.
sure.
Is it okay if you go over, let's say, if you follow the table, it's 3.14 and I want to do 5 bars of 8. Is
Uh-huh.
that over design or is it wrong per se?
No, it's not wrong per se unless you have so much steel that you no longer meet the ductility requirements, which is what we're going to talk about in a minute.
Oh, okay.
So there is a limit. You can over design your beams, and the only side effect or the only downside to over designing your beams is that your designs have to be paid for by your customer. So if what you need is 4 number 8s and you say, well, I just want to be extra, extra safe, I'm going to put 4 number 10s. Well, somebody's paying for that. And the steel is by far the most costly ingredient in your reinforced concrete. So going from 4 number 8s to 4 number 10s, if you don't need to, is an unnecessary cost. That would be the immediate effect of just over designing everything. You know, anybody could do that. If you only need is a 2x4, why put a 2x8 in there? You're just making it more expensive for somebody.
So it's like economical factors only.
Yes, until you put so much steel in there that you actually start affecting the performance of the beam, in which case you cannot do that. You get to a point where ACI draws the line and says, no, you can't put that much steel in the beam.
Okay, makes sense.
Okay, and we'll talk about that after the break, which is all part of the ductility requirements. Any other questions about this example? Okay, great questions, good participation. It's 6 o'clock. Why don't we take like a 10-minute? Why don't we come back at 6:10? Just a little short of 10 minutes, but let's reconvene at 6:10 and we'll pick it up from there. All right, we are back. Okay, so this section is has to do with ductility requirements. And we are going to identify 3 failure modes. This is still beams and flexure, but 3 different ways that beams can fail in flexure. We start with our lightly reinforced beams. So members can fail suddenly if the capacity, M sub n, is less than the cracking moment. So if the capacity of the beam is less than the cracking moment, then once the beam cracks, it will also and suddenly fail. So remember, we calculated the cracking moment. That's the moment required to create the first crack in a beam. Well, what if you had like a big old beam with just a couple number 3s in it, really small rebar? So say like it took 400 kip feet just to get that beam to crack. But once that beam does crack and you calculate the capacity, and the capacity is only 200 kip feet with those 2 number 3s, well, then once the beam cracks, it's done. It's already failed. So that's a sudden, without any kind of a warning, that would be a sudden and explosive failure. So the code does not allow that. So the code does not allow you to provide too little rebar. Again, it really not has anything to do with the capacity being greater than the demand. It's that if the beam ever did fail, it would fail in a non-ductile way. It would fail suddenly. So that's not allowed by the code. So ACI 318, section 9612, specifies that we have a minimum steel for beams as AS minimum is 3 square root F prime C over Fy BWD, or AS minimum is 200 over Fy BWD, whichever controls, whichever is greater of these two is the minimum steel that you have to provide. In this equation, BW is defined as the beam width for a rectangular beam. So if you have something that looks like this, then BW is the same thing as B. But if you have a T-beam, then it's defined as the lesser of the width of the flange, the big wide spot, or it's defined as the width of the web of the T-beam times 2. Okay, so it means something different when you have a T-beam as to when you have just a regular rectangular beam. And we'll get back to that later when we get into specifically designing for T-beams. ACI 318 9613 does allow that the minimum steel can be waived if the AS provided gives you at least 1/3 more capacity than is needed by design. So if you can show by calculation that your capacity is at least 1/3 greater than required by design, then you can use that steel even if it's less than the minimum steel. But again, we're just providing this factor of safety against the beam failing suddenly. Okay, then our next failure mode is this thing called under reinforced, which at face value seems like a bad thing. Oh, I don't want my beams to be under reinforced. Actually, under reinforced is allowed and preferred by the code. In fact, it's the only one of the 3 failure modes that's even allowed by the code. So under reinforced is good. It's not lightly reinforced. It has the minimum steel as required, but it's still known as under reinforced, as opposed to the last one that we'll talk about. So under reinforced, based on the strain diagram, the rebar will yield prior to the concrete reaching the ultimate strain of 003. So in a strain diagram, if you calculate a strain diagram for a beam that is under reinforced, you'll find that when the concrete reaches 003, that epsilon s, the strain in the steel, will be preferably more than 0.005. Rebar yielding first is good. This is the good situation. This is what we want. When a rebar yields, it causes the beam to crack and to deflect. Lots of cracking, lots of deflection, giving plenty of notice of any kind of impending problem. There's all kinds of reasons why a beam might be overloaded. Some of them may have nothing to do with the designer or the engineer or the builder or anything like that. There's just a random world. There's things that happen that once in a great while could really overload somebody's beam design. Classic example that I've seen more than once is we design a lot of parking garages. And parking garages that we design are designed for light duty passenger vehicles. We design for about 40 pounds a square foot for light duty passenger vehicles. These vehicles are meant to be about 6,000 pounds or less. I have had parking garages where somebody drove a garbage truck or a dump truck or a cement truck up onto the deck. A deck designed for 6,000 pounds generally does not do well when you drive something that weighs 60,000 pounds onto that deck, and you will overload stuff. So the point being, it happens. Not very often, hopefully, but it does happen. The point is, if you have designed your beam properly to be properly under reinforced, then when that cement truck goes up on the deck, those beams will crack, those beams will deflect, chunks of concrete will fall out. People will see that and go, you know what? I'm getting out of this building right now. And it gives people the opportunity to get out before something really, really bad will happen. So this is required by code that our beam designs are under reinforced. Then we have what's known as over reinforced. So here I got a whole bunch of steel in the beam. And over reinforced, this is one of those things where a little bit is bad, a medium amount is good, too much is also very bad. Over reinforced is not allowed and can be very dangerous. So the problem with over reinforced is that you have so much steel here that based on a strain diagram, the rebar will not yield prior to the concrete reaching the ultimate strain of 0.003. So if I look at a strain diagram with too much steel, when the concrete hits 0.003, the strain in the steel has not yielded yet. The steel may be at 40, 50 KSI. It hasn't even yielded yet. So what's the problem? Well, this presents a dangerous situation where the beam capacity is limited not by the steel, but by crushing concrete. And if it reaches its maximum strength allowance, then the beam will fail when the concrete crushes. There's no cracking, there's little deflection, there's little signs that something is just about to fail, and then it fails. And when it fails, the concrete crushes and the beam and the structure is on the ground. And there's no time to get out. There's no time for people to be distressed or get shoring in there or to get the load off of it. Whatever the issue is, there's no time to fix it. So this is not acceptable and not allowed. So what the code does to prevent this is code section 9331 prescribes a minimum strain that you must achieve in design of 0.004. So epsilon sub t, Remember, epsilon sub t is the strain in the lowest layer of steel. And that lowest layer of steel, when the concrete gets to 003, the steel has to be at least 004. ACI table 2122 puts a penalty on designs where epsilon sub t is less than 005. So really, the code wants 005 or more, but they allow for it to be 004, like a little buffer zone between 004 and 005, but you take a hit on your phi factor. And this was what I was talking about a little bit earlier, where I said most of the time, 99% of the time, phi is equal to 0.9 for flexural beams. But if you are in this category where you're between 004 and 005, then phi is reduced. If epsilon sub t is less than 005, then table 2122 prescribes that phi is equal to 0.65 plus 0.25 epsilon t minus epsilon ty over 005 minus epsilon ty, where epsilon ty is the yielding strain of your steel, which is equal to the yielding stress divided by the modulus, which is 29,000 KSI. So if epsilon sub t is greater than or equal to 005, then phi is equal to 0.9. And there is no limit on how big epsilon t can be. There is no limit. It just cannot be smaller than 004 or smaller than 005 without a penalty. If epsilon sub t is less than 004, and this is in beams now, in columns it's a different story, but in beams it's flat out not allowed. If you calc this out and you get a strain of less than 004, you can't use it. You have to redesign the beam. You got to take some steel out, or you got to make more concrete in. One or the other, you got to get this strain to be greater than 004, or you're not in compliance. You can't make that beam. Okay, any questions on this concept?
Yeah, Professor, can you please explain why it's bad again?
Okay, it's bad because beams only give you a lot of warning that something really bad is happening when the rebar is yielding. When the rebar freely yields, it's basically stretching under a constant load, the yielding stress. And when that rebar gets to a point where it's yielding and it's just stretching, then the concrete itself will crack really wide. And you'll have lots of cracks, and they'll be really hairy, scary looking cracks. And so anybody in that structure who can see the beam will notice, my goodness, that thing's really deflecting, and those cracks are really scary looking. I think I'm going to leave this building now. But if the rebar does not yield, then you don't see the cracks. You don't see the big deflection. You don't see anything until the concrete hits this crushing strain, and then suddenly, and I do mean suddenly, the beam fails and it collapses. Anybody inside will not survive. See the difference?
Yeah, thanks.
Okay. Any other questions on this concept? Under reinforced, over reinforced?
So it's kind of giving you like a warning sign.
Absolutely. That's the whole point.
Okay.
I had a question about the penalty on the design. Like, is that like, are they like referencing like for like what kind of penalty are we like talking?
Okay. All right. So remember the example that we just did where the demand was 375 kip feet, and I provided 4 number 8s, and I provided 376 kip feet. So everything's fine, right?
Mhm.
But what if the demand was something more like 1,000 kip feet? Okay, so I would go through that process of example 3 that we just did, but I would come back and say, oh my goodness, I need 10 square inches of steel. So, okay, no problem. I'll provide 10 number 9s in this thing, right? So I'm actually showing 12 here, but say I provide 10 number 9s and the rows are stacked up like this. So you might make the mistake of saying, well, I provided 10 square inches of steel. The design demanded 10 inches of steel. I'm done. Everything's fine. But that would be a huge mistake because one, 10 inches of steel is a huge amount of steel. And that huge amount of steel means that the compression block is going to go way down in here to balance all that steel. So that when you calculate your strain diagram, first of all, you may get a strain that's even lower than 0.004. So you may have a beam that's just flat out in violation. You can't do it. But you may also get a beam, maybe the beam's not at 0.004, but maybe it's at 0.045. Okay, so it's in this middle ground. Well, you assumed when you calculated that you needed 10 inches squared of steel, you assumed that your phi was 0.9. But if you calculate it now your phi is only 0.78. Oh, so 10 inches of steel doesn't even work anymore because the phi went down. So now I need 12 inches of steel. And 12 inches of steel definitely doesn't work. See, you're going down this path. What the code is trying to tell you is it's not working. Don't do this. But it does give you this little bit of a buffer zone so that you can figure out exactly where you are with your penalty. But what it's really trying to get you to do is don't design it for 1,000 kit feet. That's too much. Or make the beam bigger and deeper, and then you can handle it okay.
Okay. I get what you're saying. I got it.
Does that make sense?
Yeah, no, that makes perfect sense.
Okay, great. So again, the whole point of this whole exercise, the code put a lot of effort into guiding folks away from this dangerous situation. They give us a little bit of a buffer zone that adds some complexity to what we're doing. But really what they're trying to do is we don't want you anywhere near this over-reinforced condition, and we're not going to let you get there. So they're really kind of just forcing you back into the under-reinforced category. That's where you want to be. And most of the time, you are. Most of the time, it's not a problem. Okay, let's see. Oh, okay, so how do we calculate epsilon sub t? We need to calculate it in order to do this check. How do we calculate it? Okay, so what we do, it's all based on the strain diagram. So remember, at this point here, the strain at the top of the concrete is a fixed number. That's always 0.003. So that's been given to us. But how do we find out what epsilon sub t is? So what we do is we say that by similar triangles, epsilon sub t plus epsilon sub u over the whole d is equal to epsilon cu, or I use these interchangeably. This is epsilon u or epsilon cu, same thing, over c. So that's just similar triangles. This triangle to the whole triangle. Solving epsilon sub t is equal to d times epsilon cu over c minus epsilon cu. And I can consolidate that is equal to epsilon cu d over c minus 1. And I can plug in, because epsilon cu is always going to be 0.003. So I can plug in 0.003 d minus c over c. That's my equation for epsilon t. But I don't have little c, do I? How do I get little c? Well, first of all, per code, again, there's no maximum value for epsilon sub t. You can get 0.15, you can get 0.100. It doesn't matter. There's no maximum value. There's only a minimum value. Okay. Oh, So how you get C, I'm going to do some examples probably later on, but you calculate little a, from little a you get C, and then you check this. If you have epsilon sub t less than the yielding strain, which is that over-reinforced condition that I just explained is unacceptable, then you are in what's called compression controlled. It's really more like a concrete column than it is a concrete beam. If you are between the yield and this magical 005, then you're in what's called a transition region. And again, you can only use a part of that. You can only use from 004 to 005. If you are greater than 005, so epsilon t in the steel is greater than 005, you're in this region called tension controlled, and that's where the code wants you to be for designing beams. Okay, so let's find a phi factor and check our maximum reinforcement. So here's my beam, looking pretty familiar now, 18 wide, 30 deep, steel's at 2.5 inches. And with 6,000 PSI concrete and our 4 number 8s that we got last time, is the phi factor, what is the phi factor? And are we okay with our maximum reinforcement? Okay, so the reinforcement that we chose is 4 number 8s. So I have 4 times 0.79, 3.16 inches squared. My tension is ASFY, as we said. So it's 3.16 times 60 is 189.6 kips. D is 27.5 as given. B is 18. Therefore, little a is ASFY over 0.85 F prime CB. Plug in my values, I get little a is 2.07 inches. C is little a divided by beta 1. That's that proportional relationship between the Whitney stress block and the distance to the neutral axis. Beta 1, if I plug in for 6,000 PSI concrete, I get 0.75. So therefore, little c is 2.07 divided by 0.75 is 2.76 inches. Now I can plug into my epsilon sub t is 003 d minus c over c. So I put in 27.5 minus 2.76 over 2.76 is 0.279. 0.269 is actually much greater than 0.05. This is like 27 to 5. So therefore, we're okay. Since epsilon sub t is greater than 0.05, phi then is just flat out 0.9. It's never more than 0.9, but it could be less than 0.9 if you are less than 0.05. But in this case, we're well above 0.05, therefore phi is 0.9. And that's it. That's how we know that we are under reinforced. So if I was to ask you on this problem, are we over reinforced or are we under reinforced? The answer is clearly we are under reinforced because I have a epsilon sub t greater than 0.05. That is my definition of under reinforced. Any questions on this problem?
Professor, just for clarification, the 2.07 is from the top going down, right?
Yes, it is.
Okay.
That little a is our definition of the Whitney stress block. So the Whitney stress block goes from the extreme concrete in compression, which in this case, the compression's in the top, the steel's in the bottom. So that goes from our extreme fiber in compression down to the bottom of the assumed Whitney stress block. So yes.
Okay.
And then little c, of course, is from the top fiber in compression to the neutral axis. Any other questions on this problem?
Can you repeat the C again?
Little c is from the top fiber to the neutral axis. There, let me go back to a strain diagram. Little c is from the top fiber to the neutral axis. Neutral axis is the definition of where the strain is equal to 0.
Right. Okay. Well, that makes sense.
Got it?
Yes.
Okay. Okay, now let's talk about rebar placement. So when we make a concrete beam, rarely do we ever have just flexural reinforcement. So the circles that you see here, what am I representing? Well, I'm representing if I had a concrete beam and I took a big old giant concrete saw and I cut that beam in half and I'm looking into it. This is what I would see. So when I cut that beam in half, all the rebar that is running from one end of the beam to the other end of the beam will be cut in half as well when I cut through that. That's what these circles are. So the circles represent my flexural reinforcement that runs from one end of the beam to the other end of the beam. This bar here is what's known as a shear tie or a tie. It could just simply be called a tie. And the shear ties are here for the purposes of shear design, which we'll talk about in a couple weeks. So we're not anywhere near talking about shear design yet. But it is important that you realize this is how we build a beam so that the longitudinal or flexural reinforcement goes in and out of the page. The shear ties are in the plane of the page. And when we build the beam, it looks just like this. We have a whole bunch of these guys at some regular spacing from one end of the beam to the other. And inside of these, we have the rebar that is longitudinal from one end to the other end of the beam, okay? It's important to understand that these ties are in here because we have to provide a certain amount of concrete coverage around these ties. So the clear cover is determined by design. This is, see how it's labeled here? That's the concrete coverage. You can't have this steel too close to that exposed edge for corrosion and for fire issues. So we typically take that this concrete clear cover is 1.5 inches. That's like a, not everybody does that, but that's like a very common coverage to call out for is 1.5 inches. And for the purposes of this class, if I don't tell you what that concrete coverage is, you can assume it to be 1.5 inches. That's just a very common. But it may be more than 1.5 inches. It may be less than 1.5 inches based on certain circumstances. Okay, so it's not always 1.5 inches, but that's the most common thing that I see. It may be more or less than 1.5 inches for corrosion protection or for fire protection. So if you had this steel too close to the edge, or if you actually had the steel exposed to the edge, then depending upon where you live or where this beam lives and what's happening in that part of the country, some parts of the country are exposed to much more corrosive environments than other parts of the country. Down here in Southern California, we enjoy a very uncorrosive environment, but up in places like Michigan or Chicago, where they have to put de-icing salts on everything, you could get a very corrosive environment. And in which case 1.5 inches isn't even close to enough coverage. All this concrete will eventually blow off and the rebar will rust. But even in Southern California, there are situations where you need more coverage than that as well. Situations like if you built a concrete structure that is at or near the surface of the ocean, That's very corrosive. You'll need more coverage. Or if you build a concrete structure that is exposed to some sort of a man-made environmentally corrosive environment, like wastewater treatment plants or anything exposed to, airborne nasties, may need more corrosion protection. And you have to provide a certain amount of fire protection as well. How much fire protection you need is basically determined by architectural constraints and the code. But the more concrete coverage you provide, the longer this beam will resist the heat of a fire before the steel inside gets so hot that it loses its strength and properties. Okay, so all of that is to say that the clear cover around these ties usually is 1.5 inches, but could be more or less depending on circumstances. The side cover, as I've shown here, is typically the same as the bottom cover, unless you have some special conditions that require something other than a uniform thickness all the way around. Okay, so now what I've done is I've taken that beam and I made it bigger so you can kind of see what's going on here. The side clearance, which is the center of the first row of steel to the outside of the tie, can be taken as the larger of. You can consider it to be 1/2 dB plus dBt, or 3 times dBt, whichever is larger, where dB is the diameter of the flexural steel, so that's the diameter of this longitudinal steel here, and dBt is the diameter of the transverse or shear tie, which is here. Okay, so whichever of these two controls will tell you what your dimension is from the center of the steel to the outside of the tie. And what this is going to do is I'm giving you tools so that you can figure out, given a width of concrete, how much steel can you put into a certain width of concrete? Or how wide does the beam need to be in order to carry the rebar that you want to carry? So for instance, say like the design calls for 5 number 10s. Well, how wide does the beam need to be to fit 5 number 10s? Okay, so how wide does the beam need to be? Needs to be the side cover plus this distance from the center of the rebar to the outside of the tie, plus the space between them, plus the diameter of the bars. And then of course you have this on both sides and you have the side coverage on both sides. So you need to add up all these pieces in order to determine the minimum width of the concrete to carry the rebar that you want to carry. The clear spacing between the rebar is defined by the code. 2521 prescribes minimum clear spacing inside face to inside face of the rebar in a single layer as the greatest of 1 inch or 1 bar diameter or 4/3 of the diameter of the aggregates, where the dAg is the nominal maximum size of the coarse aggregate, right? So if you're using like a 1.5 inch rock, then this could be a pretty big space. Usually this won't control. Usually the provider of the concrete knows about this rule, so they will size the maximum size of the aggregate in the mix for this structure based on how much space you give them, right? So if you make the space only 1 inch, then they know that the rock can't be more than a 1/2 inch maximum or something like that. Okay, so given these rules here, 1 inch or the bar diameter, if that's more than 1 inch, tells you what this space needs to be. So now you can add up. You can add up the side cover, both sides, the center of the rebar to the outside tie times 2, plus then you have 1, 2, and a half, so 3 bar diameters plus 1, 2, 3 spaces. You can add all those up, and that will tell you what the minimum width of your concrete beam needs to be. The required clear spacing in the vertical sense, ACI 2522, prescribes the minimum clear space or rebar between layers as just simply 1 inch. You need to provide an inch between those layers. Table A5 in that appendix, page 597 of the text, will give you a summary of required minimum widths of beams to accommodate the number and size of flexural steel. So we have a cheat sheet, something that is quick and dirty instead of adding up each one of these. I believe in the homework, I asked you to do it by hand the first time. And then anytime we see this in the future, you can use the table. But I want you to do it by hand at least one time, so you go through the mechanics of it. ACI 318-2613 provides prescriptions and tables that dictate the minimum concrete cover for corrosion protection. Additionally, ACI 318-19.3 gives some concrete mix requirements based on exposure, and the fire cover requirements are actually in the IBC or CBC code, a totally different code, and that's where you find your fire protection requirements. Okay, so example number 4. Let's find the allowable flexural capacity of the following beam. So this beam is 30 inches deep, 18 inches wide, but it's got a lot more steel. I got 3 number 9s and 3 number 10s. 3 number 9s in that row, 3 number 10s in the bottom row. And I actually drew this all to scale. That's why these numbers are to such precision, 25.19, 27.38. So what we want to know, when I say allowable flexural capacity, that's code. That's code speak for phi mn. That's what that means. If I say the nominal flexural capacity, then that's just mn. But allowable flexural capacity is phi mn. Okay, that's the difference. If I have 3,000 psi concrete and I have 3 number 10s and 3 number 9s, grade 60, what is the capacity of the beam? Solution. All right, so the total area is 3 times the area of a number 10 plus 3 times the area of a number 9, gives me 6.81 inches squared. My d sub t to the lowest level is 27.38. The little t, epsilon t, d sub t always refers to the lowest row. A is ASFY over 0.85 F prime CB. I plug in my values. There's my 3,000 PSI concrete. And A, little a, is 8.9 inches deep. That's my Whitney stress block. Little c, distance to the neutral axis, is A over beta 1. Beta 1 for 3,000 PSI concrete is 0.85. So little c is 8.9 divided by 0.85 gives me 10.47 inches. So that my strain, epsilon sub t, is 0.003, 27.38 minus 10.47 over 10.47. Oh, well, we're at 0.0485. So the good news is the beam is still legal because it is greater than 0.04. But we're going to suffer a penalty on our phi factor because it's also less than 0.05. So I have to calculate what my epsilon, my phi factor is. epsilon ty, the yielding strain, is 60 over 29,000, is 0.0207. So my phi is 0.65 plus 0.25 epsilon t minus epsilon ty over 0.05 minus epsilon ty. I plug in epsilon t, epsilon ty, epsilon ty, and I get 0.887. I also need to know, where is my d? D sub t to the lowest row is 27.38, but D is to the centroid of my steel, and that's not obvious. So I'm going to do a weighted average of the 3 number 10s at 27.38 plus 3 number 9s at 25.19 divided by the total area. My effective D is 26.42. So now I'm ready to plug in my nominal moment equation, where I have 6.81 times 60 d as fy f prime c b, and my nominal moment is 89.77 kip inch, or 748 kip feet. That's my nominal capacity, but I asked for allowable capacity, so I need to multiply this times phi. Phi is not 0.9, as we just calculated, it's 0.887 times 748 is 663.5 kip feet. That's my allowable capacity. And you can see how I've added so much steel that I'm really suffering a hit by having a phi of less than 0.9. So this is not ideal. In real life, I would add some depth to the concrete or do something else. I wouldn't have something this close, but it is legal. I can use that value. Any questions on example 4? All right, that is my presentation for tonight. Last chance, any questions on the material that we talked about? And may I remind you, we're already more than 10% into this course. This is going really fast. So I beg of you, if you have questions, read the text, review these lectures, watch the YouTube if you're an audio learner, read the PowerPoints if you're a visual learner, read the text again. And then if you have any questions at any time, please interrupt me to ask those questions. So, does anybody have any final questions?
I have a question, Professor.
Great.
So for FY, is it the 60 KSI? Is that the grade?
It is the grade, yes.
Okay, yeah. And that one is always in KSI, right?
Well, it's yes, no. When I report it like an ASTM standard, A706 grade 60, yes, that's always KSI. That is correct.
Okay. And just to clarify that one, okay.
Yeah. Now, when you do your calculations, if you prefer to use PSI, there's nothing wrong with that. I think the text may do that in cases where instead of 60 KSI, you're welcome to use 60,000 PSI and 60,000 PSI here, but you have to keep your unit straight. Then you have to use 3,000 PSI for the concrete so that your units come out straight. And if you do that, then what you'll get is the same answer, but your answer here will be 89,770 pound inches instead of kip inches, right?
Right.
Which is not a problem. You just got to be cognizant of your units, which is true in any engineering course. You always have to be cognizant and careful of your units.
And then for D, it's just basically like the middle ground for the area of the top part and then the bottom part, right?
Yes. Yeah.
Distance from the top to the middle of that two rebars.
To the centroid.
Yeah. Mhm.
Now, if most of the time the rebars are kind of equal, like 3 number 10s and 3 number 10s, in which case you can just eyeball,
In
you
the
know,
middle.
halfway between them, that's no problem. But if they're not equal, if you have 3 number 10s and 4 number 10s, or 3 number 9s and 3 number 10s, if they're not equal, then you have to do this weighted average to calculate where the centroid is.
Right. And
Yes.
for spacing, vertical is always 1 inch.
1 inch between them. So it's a half a bar diameter, 1 inch, and then half a bar diameter again.
Ah, okay. Oh, I think that's it. Okay.
Okay, good
Mhm.
questions. Anybody else? All righty, not hearing any, then we'll wrap it up for tonight. I bid everybody a good weekend. And if you want to see this on YouTube, I will post it tomorrow morning. So good night, everybody. We'll see you next week.
Thank you, Professor.
Thank you, Professor. See you next week.
Thank you. See you next week.
See you next time, Professor.
Thank you.